Hey guys, Mr. King here. Today we're going to be talking about the Earth's weather, and this is kind of building on what we've already talked about with the atmosphere. We've talked about how the troposphere is the layer where all the Earth's weather is going to be occurring. So today we're going to talk about why we have the different types of weather that we do. We're going to talk about differences in temperature, and we're also going to get into precipitation and how much water vapor there can be in the air at one time. So we're going to try to figure out what determines the weather outside. Why do we have the weather that we have? So our weather is the atmosphere's current condition. It includes temperature, cloud cover, wind speed and direction, humidity, and air pressure. So if I ask you what the weather's like outside, most people just stick with the temperature. Most people just say it's either warm or cold. But there's still a lot of other aspects of it that you need to include. Our weather involves a lot of different areas. So it's not just, oh, it's a really hot day outside or it's a really nice day outside. If you were to thoroughly describe the weather, you would have to count on all these things. You'd have to talk about the temperature, whether it's cloudy or not cloudy, whether it's windy or not. If when you step outside, if you can feel that it's humid or if there's a lot of water vapor in the air. And the air pressure, are we having a lot of air pressure pushing down or not a lot? And that's associated with a high pressure system or a low pressure system, which gives us cold and warm air. So there's a lot of different things to take into account when we're talking about the weather. Most of us are pretty content with just knowing, is it going to be warm or cold? If you ask your parents, what's the weather going to be like today? Can I wear shorts? That's pretty much the only thing you're concerned with. So it goes a little deeper than that. So temperature is the first one. Like I said, this is probably the one most people are most concerned with. As we've learned, temperature is a measure of the kinetic energy of the atoms in an object. So it's a measure of how fast the air molecules are moving. If the air molecules move really fast, temperature is going to be high. And you guys know the faster they move, the higher their kinetic energy, and when they bang into each other, they're creating friction. And so when you've got a whole bunch of molecules zooming around banging into each other, you're going to have a really high temperature. On the opposite side, if you have a bunch of air molecules that are moving around pretty slowly, you're going to have cooler temperatures because they're not moving around as quickly and they're not banging into each other and releasing as much heat. We've got two scales that we use, Celsius and Fahrenheit. You guys know we're one of the few countries in the world that uses Fahrenheit. We also have a Kelvin scale which scientists use to measure temperature. But for us, Celsius and Fahrenheit are good to let us know what the temperature is going to be like. And for you guys, unless you move to Canada or Mexico, Fahrenheit's going to be what you're going to use for probably the rest of your life. You probably won't use Celsius a whole lot. So our energy transfer happens when fast-moving and slow-moving molecules hit each other. When they bang into each other, that is conduction. We've talked a lot about that. We talked about that on the last video where we talked about how when the sun shines down on the earth, it warms up one spot, and then that spot, those molecules start to bump into each other, and they start to bump into the others, and they start to bump into others, and the heat is released from the ground of the earth. Now, as that heat is released from the earth, that's where convection comes into play. Convection is when the warm air rises and the cool air sinks. So as the conduction happens on the Earth's surface, it starts to warm the air right by the ground, that warm air starts to rise up. That warm air rises up and up and up. And if you remember, as you go up in the troposphere, it gets colder. And so as it goes up and up and up, it cools, it cools, it cools, and then once it gets cold enough, it sinks down because it becomes more dense. So here's me drawing a little bit about it and talking about the difference between warm air and cold air will help us to understand the difference between this. And when you've got warm air and cold air, you have a difference of air pressure. And air pressure is the air weight that varies over the Earth's surface. Now warm air is less dense and it exerts less pressure, and cold air is more dense and exerts more pressure. So it actually pushes down harder. And check this out. This will kind of help explain it a little bit and you guys can see what's going on. Alright guys, so we're talking about warm air and cold air and how they're kind of different. So if you look at cold air and you think about the way we've talked about solid liquids and gases, cold air is going to be much closer to being a liquid, because as you cool down a gas, it becomes a liquid. If you can make a gas cold enough, you can actually turn it into a liquid. Now, on the other hand, if we want to talk about warm air is kind of the opposite. Warm air is spread out quite a bit, and the particles are moving around a little bit more, and even though they're both a gas, you can see they're actually spaced out quite a bit differently. And so with cold air, you can see over here, with cold air you get more pressure because it's more dense and it's pushing down on you. You can see these particles are a lot closer together, and that's going to be a more dense and a higher pressure. Warm air is much more spread out, and so the warm air is going to be rising, and that's less pressure pushing down on you. They're actually floating upwards, so that would be a low pressure system. So even though these are both gases, they look differently. Gases can be spaced out differently depending on their temperature. So cold air packed together really tight, and warm air is not packed together really at all. It's more spread out. So as you guys can see, there's not a whole lot of similarities between warm air and cold air. They're actually really different. And when you have cold air, you have a high pressure system. If you guys have ever seen a weather map, the high pressure system is the big blue H. And usually with that big blue H, you get colder air. The warm air is usually a low pressure system by the red L. And the reason why it's red is because red usually means warm. That's why I drew in these colors. So they are very different in the way they act in the atmosphere. Warm air is rising up, so that's not going to create a lot of pressure on you pushing down. Cold air is sinking down, so that's definitely going to create a lot of pressure. So with the amount of water vapor in the air, it affects a lot of different things. Humidity is the amount of water vapor that is in the air at any time. And the temperature affects how much moisture can be in the air. If you look back at this diagram, warm air is much more spread out, so you can have a lot more precipitation in there. You can have a lot more water vapor stored up in there. Cold air is a lot closer together, so there's not as much room for water vapor. Dew point is when the air is holding as much water vapor as it can, and relative humidity measures how much water vapor is in the air compared to how much could be there. And I'm going to draw a couple things for you guys to help you understand those different things. There's a picture of some random kids for you. And it'll help you understand this a little bit better because it's kind of confusing. So when we've got our warm air and cold air, I'm going to draw cold air first. And kind of like we've already talked about, cold air is really spread out, or really close together, excuse me. And it's dense, and this gives us that high pressure system. Okay? And warm air, on the other hand, warm air is low pressure, and it's pretty well spread out. So when we're talking about the amount of water vapor that could be stored in here, I'm going to make my water vapor green just so it shows up so you guys can see it a little bit better. The words that we're talking about, humidity is the amount of water vapor in the air. Okay, so let's imagine it's a really humid day out. That would mean there's a ton of water vapor in the air. Now on a warm day, you can squeeze in tons of water vapor because the air is really spread out. On a cold day, there's not much room. I can maybe get a couple in here, but you can already see I'm pretty much out of room because the cold air is really dense and packed together. So temperature definitely affects how much water vapor can be in the air. Now what's going to happen is once these get filled in and this whole thing is contained with water vapor, you're going to get rain and it's going to come out. And you can see this can't hold much. If you think about this as being a cold air cloud versus a warm air cloud, this warm air has a lot of room for a lot of water vapor. And once this fills up, we're going to have a really good rain because it's got a whole bunch to start with. When it's cold out, you don't really have a good amount of precipitation because there's not a whole lot of space to store it in. Now dew point is when the air is holding as much water vapor as it can. So I would say this is pretty close to the dew point for both of these because they're pretty much holding all they can hold. You can see that's going to be the point when they create dew or when they create moisture. Okay, so there's no more room. Water vapor can't evaporate anymore. It's time to release that, and it's got to get rid of it. And so that's the dew point, is when it's going to be all filled up. Now, the last thing is called relative humidity. Okay, and relative humidity I'm going to talk about with warm air, because it's a little easier to see when it's all spread out. Relative humidity means how much water vapor there is in the air versus how much there could be. Okay, so I'm going to stick with green as being our water vapor, our precipitation. Okay, if you look at this, at this point right now, I would say the relative humidity of this warm air is pretty low. And the reason why it's pretty low is because there's not a whole bunch of humidity or water vapor in here. There's a lot of room still. Okay, if I want the relative humidity really, really high, and these are the days when you guys go outside in the summertime and it feels really sticky, it's because there's tons of water vapor in the air. And the reason why there's tons of water vapor is because there's tons of space, because it's hot out. And so the air molecules are really spread apart. So if I wanted a high relative humidity, this is more what it would look like. Okay, this would be a super high relative humidity, because you can see this is holding almost as much as it could possibly hold. There's almost no room anymore for any more water vapor. So that's a really high relative humidity. And when that happens, when the relative humidity is high, you're going to get some rain. It's going to come down. Now, the other way that you get rain is if it gets colder out. Let's say it gets colder out. What are these air molecules going to do if it gets colder? They're going to become more dense, and they're going to shrink in. And they're going to get packed closer together, almost like a cold group of air. And when you sink them in, they're going to squeeze out that water vapor because there's not as much room. So you can be guaranteed you're going to get a lot of rain if you have a really warm day that starts out with a ton of relative humidity, and then the temperature drops. When the temperature drops, those air molecules get closer together and they squeeze out that water vapor. That's why when a storm is coming in, you can feel the temperature drop. You feel that kind of cool breeze kick up. It's because there's cold air coming, which has caused the warm air to condense and squeeze together, and it's got to get rid of that water vapor to make more space. And that's really a good telltale of when that weather is going to change. You can feel that front coming through. All right, guys, hope this makes sense. Have a wonderful night. Make sure you get your quiz done on the back. Write some good questions. Once again, with weather, it's always fun to think about the what ifs. What would happen if this? So make some good thoughts, and I will see you guys tomorrow.